The third and last section of chapter 5 talks about LAN switching. So here we will cover all the issues related to LAN switches and how they work. As we said before, that the switch implements a physical topology of star topology that connects all the nodes to the switch, whereas in logical term, the switch forms that multi-axis bus that connects all these nodes together. So if we want to send data from let's say H1 as a source and H6 as a destination, the switch will then receive the frame from the source, checks or looks up the destination address in the MAC lookup table. And one thing to notice here or to observe is that the MAC table is separate and different from the ARP table. Well, the ARP table is stored as a cache on each node, whereas the MAC table here is stored inside the switch. So that's one thing we need to highlight here. So to understand how the switch actually works, the switch performs a certain procedure how to switch or forward the frame from a source to a destination. So if we were to assume that PC1 wants to send to PC3, the frame will contain the source MAC address and the destination MAC address. So the first thing the switch does is that it receives that frame on port 1. So at the beginning, the way that the MAC table gets formed is that the switch initially will have empty MAC table. So it does not really know which PC is connected to which port. When it receives that frame on port 1, that's one piece of information that it actually learns. So in step 1, the switch will receive the frame on port 1, so it knows that PC1 is connected to port 1. Why? Because the frame is coming and the source MAC address is stored in that frame. So so the MAC table will now have one piece of information, the fact that port 1 now connects PC1 to it. So that's one piece of information that the switch will learn. Again, at the beginning, when the switch looks up the destination MAC address, which is the MAC address for PC3, it finds that it does not have this entry in the MAC table. So it doesn't know whether this destination address is connected to port 2 or port 3. In which case, what the switch does is that it will broadcast or it will send the frame on both ports except the port that the frame came from, which is port 1. So the switch will send or broadcast the frame on all ports. In step 4, of course, because the frame contains the destination address for PC3, only PC3 will reply back with the reply to PC1. So now the source address will be PC3 and the destination address will be PC1. So now the switch will learn that PC3 is connected on port 3, and it updates that in the in port 3 in the MAC table, and it keeps doing that until it learns all the MAC addresses for all the PCs that are connected on the different ports. Once this MAC table is formed, then and only then the switch will use unicast to send the frames to the particular port address based on the physical address. So these are the steps on how the switch will learn the MAC table. As we have mentioned before, there are two modes that the connection or the physical medium will work from one node to another, from the switch to a particular node. If there is a hop in between, then by default we work in a half duplex mode, which means that the switch and the node, you cannot send and receive from this node at the same time. So you have to use the connection between the switch and this node either for sending or receiving. And if it happens that you try to send and receive at the same time, then collision will happen. That's what we have highlighted before as one-way street, and you can use it either in this direction or in this direction. So you can use it either for sending or receiving. So to allow for one only direction to be used at certain time, we use technique like Sysmus CD to resolve collision in case that we try to send and receive at the same time. The full duplex mode on the other side, it gets represented by a switch. So whenever you have a switch, both connections will be full duplex, which means that we can send and receive at the same time on these links. And that gets represented by a switch. Well, as we will learn in the lab, that the switch can actually work either as a full duplex or half duplex. So it can downgrade itself to the half duplex mode if needed. In which case, sending and receiving will happen by the switch using collision-free techniques. So we don't need, in that case, collision detection to detect collisions when it comes to a switch. Okay, so a switch in general can work as half duplex or full duplex, depending on the medium that it actually connected to. And one thing that recently has been developed in modern switches is that some switches can actually detect the appropriate mode on the connection here, depending on the type of media. So it can work automatically as full duplex or half duplex, depending on the connection that it's connected to. So, for example, this switch will detect automatically that there is a hop on the other side, so it uses half duplex connection. This switch will detect that there is a switch connected to it, so automatically it works as full duplex. This feature is called auto MDEX feature. So the switch has an automatic technique called auto MDEX that detects the appropriate mode of communication according to the device that is connected to it. For example, this switch is connected to another switch, so automatically it detects that it can use full duplex. This switch is connected to a router, so it automatically detects that it can work on full duplex, and so on. So if it's connected to a hub, automatically it detects that it can work only using half duplex. So this feature is called auto MDEX. The switch has two types of forwarding techniques that it can use. One forwarding type is called store and forward, and the other one is cut through. The difference between the two is as follows. Store and forward, when it receives the frame on one port, it stores the entire frame inside the switch, and it performs a complete error checking on the frame before it forwards the frame on the output port. So again, it stores the entire frame in the memory inside the switch. It performs an error checking using the CRC on the frame check sequence field, and then it makes sure that this frame is correct before it forwards the frame on the output port. The cut through, on the other side, it does not store the entire frame, and it does not perform error checking. And the cut through is used for fast forwarding or speed forwarding, so it does not store the entire frame. It only checks the destination MAC address in the frame, and then it forwards the frame directly on an output port. So in that case, the latency or the delay associated to the frame forwarding in the cut through is less. So in store and forward, the source will send the frame to the switch, and the switch will have to store the entire frame and then check the CRC and make sure that the frame is correct. And if the apply is the frame is good, only then it can forward the frame on the other side. Whereas for cut through, the switch will receive the frame, and it only checks the switching table to look up the destination address, and then it forwards the address quickly. The cut through switching is done using two possible techniques. One is fast forward switching, and the other one is fragment-free switching. The fast forward switching, in that case, this is the fastest way of frame forwarding, that the switch only checks the destination MAC address and then it forwards the frame directly. So it only reads the destination MAC address and then forward the frame directly to the output port. This has the lowest latency when it comes to frame forwarding, of course, because we don't have to read any part of the frame except the MAC address. On the other side, there is a potential risk that when you forward the frame quickly, there might be a collision on some of the connections, in which case you waste the transmission of that frame, and you have to retransmit that frame. So speed is not always good, as we can see that when we drive very fast, sometimes it increases the possibility of collision. So to have a little bit of a compromise, we have another mode which is called fragment-free switching. In fragment-free switching, the switch does not store the entire frame, and it does not forward the frame just by reading the destination address. Instead, it stores the first 64 bytes. And recall, as you can recall, that we said that the minimum Ethernet frame size is 64 bytes, and the reason for that is that if there is any possibility for collision, it happens within the first 64 bytes, as we will see later. And because of this, the fragment-free switching achieves the compromise between fast forwarding and store and forward by storing the first 64 bytes of the frame before forwarding. So if it checks the first 64 bytes and makes sure that there is no collision happening, only then it forwards the frame on the output ports. So the switch architecture uses two types of memory to store the frame. One structure or one architecture of the switch uses what we call port-based memory. In port-based memory, the switch uses separate buffer on each input port to store the incoming frames, and the buffer in that case will use will use queues. So remember, in computer architectures, queues, the storing of the frames will happen in order, and then you have to output the frames in order from the queue. So the queue has input and output, and it has to send the frames in the same order that they came on the input port. So this queue will exist on each port, and then the switch will look up the MAC table and send the frame from one input queue to one output port on the switch. Again, the queue is single input, single output, and the other type of the switch architecture is what we call shared memory. In shared memory, there is no queue associated to each port of the switch. Instead, the switch uses a random access memory that's shared by all the input ports and output ports. So the shared memory is RAM that's stored inside the switch fabric, and you can then use this random access memory to store all the frames that are coming from all the input ports, and then you can access any frame at any point in time and send it to an output port. One disadvantage for port-based memory is that it always suffers from what we call head-of-line blocking, which means that sometimes if the output port is busy sending a frame, that blocks all the frames on the input queue that are waiting to be sent to a specific output port. This is called the head-of-line blocking. So imagine if you have a queue in a bank or something, and then the first guy on the queue is taking a long time, that blocks the whole entire queue. So that's one of the problems exists in the port-based memory. Whereas for shared memory, it does not suffer from that problem because it uses random access memory. Okay, another cool feature in Ethernet is what we call power over Ethernet. And using the power over Ethernet, some devices, some end devices like Cisco IP phone and stuff, it takes its power directly from the switch. So they have very specific ports. They are called power over Ethernet ports, and they can take this power feed directly from the LAN switch. So that's a nice feature that exists in recent Ethernet switches, that there are some ports which are called power over Ethernet. And that's why all our IP phones at QU, they do not have separate power lines connected to them. These are some of the connectors that are used by the switches that will be explained in the lab. So the last topic here is what we call LAN layer 3 switching. As we recall, layer 2 switches, they use the MAC address for forwarding the frames to the proper destination nodes. And one of the problems is that the layer 2 switch has to learn all the physical addresses of these ports from the frames. To save that learning time, there is another type of LAN switches, which is what we call layer 3 switch. Layer 3 switch uses both MAC address and or IP address for forwarding the frames to the appropriate nodes. So instead of learning all the physical addresses that correspond to a particular IP address and stuff, so layer 3 switch is actually allowed to forward the packets on the LAN using IP addresses if needed. So to do that, the layer 3 switching is rather complicated, and the layer 3 switch actually uses two types of extra tables. One is called the forwarding information base, and the other one is adjacency table. Forward information base is used to store the IP addresses that are used for switching, and adjacency tables are used to store the MAC addresses or the physical addresses that are being learned through the forwarded frames. So the layer 3 switch can switch between those two tables and use either the IP address or the physical address for switching as appropriate. So if it finds the physical address in the adjacency table, it uses that for fast switching, and if it does not find the physical address inside the adjacency table, it uses the IP address from the forward information base table for forwarding, and this way you can save time on learning the physical addresses. To handle the layer 3 switching, layer 3 switches will often have three types of interfaces. The first one is what we call the switch virtual interface, and this is some type of a logical interface that connects virtual LANs. As we have explained before, virtual LANs are some type of LAN connections that group some devices together in a logical way. And the layer 3 switch will have what we call SVI interface to connect these virtual LANs on a specific port on the switch. The other type of interfaces is what we call routed port, and that's a physical port that connects the layer 3 switch and allows the layer 3 switch to work as a router, as a physical router. So in that case, the layer 3 switch will use completely the IP address to work effectively as a router port. The third type of interfaces is called layer 3 ether channel, and that port is another logical interface that allows the layer 3 switch to aggregate the bandwidth from multiple LANs or from multiple interfaces into one interface to the uplink. So this way you can aggregate the bandwidth from multiple ports to feed to a router in an aggregated bandwidth. That we come to the end of this chapter, and in this chapter, as we have summarized, we talked about the Ethernet protocol as the most common protocol on the local area networks. We talked about the fact that Ethernet includes the logical link control and the medium access control, and we talked about the issues in each one. In section 2, we talked about the address resolution protocol that is used to get the physical address that corresponds to a particular IP address for the two cases when the address exists on the local area network and when the access exists on a remote area network, and the fact that we use the default gateway for this. In the third part, we talked about Ethernet switches or LAN switches, and we talked about both layer 2 and layer 3 switches and how and what techniques and issues that the layer 2 switch uses for frame forwarding as opposed to layer 3 switch. So that concludes that part of chapter 5.